Hi, I'm Lazpita, a PhD student in aerospace engineering, and right now I'm doing my research stay here in the Harvard University. And the video today is going to reproduce the talk I gave in the Harvard University as part of the seminar of Made in the UPM. And well, as you can see in the screen, this talk is going to in this talk, I'm going to present my work on exploring hard flow dynamics, integrating CFD simulations with neural networks. In general, this is some kind of a review of my PhD thesis, the work I'm doing for my PhD thesis. So let's start first, just seeing the outline of this talk, where I'm going to introduce you to myself first, but also to the problem we're going to study in this talk. Then I'm going to give you the three main key points of my thesis, which are the simulations, the neural networks, and the reduced pattern models, and finally some general conclusions. So, as I said, I'm Lazpita, a PhD student, and well, my studies in the research field started in the bachelor's degree in aerospace engineering, where I had some interest into fluid dynamics, computer science, mathematics. So I made a project with in the department of mathematics about pattern analysis in urban flows. This was part of a collaboration of the UPM with the KTH and the Universidad Politécnica de Valencia. And from this study, we published a couple of articles. Then I did my master's degree in industrial mathematics, pursuing a little bit more this world of modeling flows and other physical phenomena, but also attached to this kind of mathematics field or computer science field. And here I did a project of flow control on turbulent channel flow, which, both of these topics I've already explained to you in previous videos. But well, we also have published an article about this. And well, lastly, my PhD thesis, also in aerospace engineering, where I'm basically trying to simulate and analyze hard flow dynamics through CFD and neural networks. This is being done in collaboration with the UPB, the Aachen University, and also now Harvard University as part of my stay. We are also writing a couple of articles about this kind of about this work. So before going deeper, as this presentation was part of a public presentation, I wanted to first give some kind of key ideas about what are the databases I want to extract and why, as aerospace engineer, is working with cardiac flows, with cardiology. And well, basically, a fluid can be something liquid, can be something gas. So it can be modeling air, water, or in the case of this study, blood. Also, these fluids can be modeled using some equations, which are the Navier-Stokes equations, and with this we can extract the mechanics of these fluids. This way we can model and obtain the flow that could be around something, that could be over something, such as the urban flows, around something such as cars, airplanes, wings, etc. Or what we are interested in the current study, inside something such as a pipe flow, or in our case, a cardiac flow inside a heart. So now that we know why an aerospace engineer is interested into cardiac flows, since the modeling, the equations, and everything are the same, why is it so important studying this kind of cardiac flows? Well, there is a great burden in the cardiac diseases, which are the leading cause of death regarding diseases, as you can see here on this graph. And 70.9 million lives were prematurely cut short on 2019 alone due to these cardiovascular diseases. And right now, the state of the art is to diagnose and treat the aftermath of these cardiovascular events or diseases. It means that once it develops, we can treat it. But what we want to obtain is a tool that can identify these diseases before it even develops, and therefore can give a previous treatment or solution. So for that, I'm part of a project called the DigitHeart project, where, it's composed of different people, such as professors, PhD and postdoc students, also doctors. And in this project, we want to create, as I told you, a tool, a software, where we can introduce some patient MRI data or echocardiogram data, some medical data we obtain from the patients, thanks to the doctors, introduce it to our software, and it can classify as a healthy or an unhealthy heart. And in the case it's not healthy, and tell us which kind of disease can have, such as diabetes, obesity, myocardial infarction, whatever. Then also when this, how this disease is going to evolve in time, so when will it be the outcome time, when will it be the cardiac arrest or whatever. And finally, some kind of pattern identification that will help also this kind of classification prediction stuff, and also understand better what's happening inside a normal heart, a healthy heart, or a diseased heart. And well, inside this project is my PhD thesis, which in the end, the aim of my PhD thesis, my project, is to enforce this kind of manual network that classifies and predicts cardiac diseases using simulation data. So for that, then I am following this kind of a scheme to obtain good databases in an efficient way. For example, first we need to obtain this kind of simulation databases using some kind of softwares, which in my case is the StarCCM Plus software. But this is really this has a really high computational cost attached. So now here in the University of Harvard, I'm working on some kind of neural network called the adaptive LED, which can help us speed up simulations using some kind of neural network to obtain the predicted snapshots with a low cost. With this, we can extract this kind of big database, collecting some cycles of the heart with enough convergence. And the final part of my project will be to use some kind of reduced order model based on HODMD to obtain first the subsequent cycles fast, but also, and maybe even more importantly, to extract some kind of flow features and patterns from this data, such as identifying the vortex ring, the recirculation, or well, different features that may be involved in the heart. And well, as I said, in the end, we want to combine this simulation CFD data with medical data and improve the accuracy of our main neural network. So, as I said, the first part of my thesis are the simulations, which I've been performing until now, and I continue working on them. But there are different things to take into account in this kind of flows, since they are really difficult and complex to model. First, it would be the geometry. We first started using some ideal geometries, which are constructed for references, and we use them for validation to know, to see how we create these vortices, how, well, if our codes are all right comparing with literature, etc. And then we can also apply them to a patient-specific geometry that are extracted from some medical data we were provided. Also, the second thing would be the movement of the heart. Of course, you know that the heart is pumping blood, so the heart is moving. But first, we tried to use some rigid walls. They were not enough. We didn't obtain this kind of good vertical structures. So now you're using moving walls where the ventricle walls are moving, as you can see in the video. And finally, for the different boundary conditions, such as the inlet and outlet, we can also use different kind of conditions, such as free flow, but the ones that we are right now using are the fixed, where we specify the inlet velocity and the outlet flow rate using medical data. And yeah. So the results of these simulations are the ones that you can see on the screen. starting from the left, we see the echo criteria, which can catch vertical structures. And what you can see in the video is the first formation of the ring, then the tilting, and the creation of the second smaller ring when we are in the second part of the diastole, which is the A wave, and finally the outflow. We can also see something similar in the vorticity plane, where we see this kind of swirls going through the ventricle, and then the outflow in the systole. And finally, in the velocity, we can see also this big recirculation that is created thanks to this vortex ring. And then again, well, this recirculation that goes down to the apex, and then we have the outflow. So we were able to obtain this kind of good databases, and we want now to speed up the obtention of these snapshots, or well, yeah, databases. So for that, as I said, I am now currently working in this kind of neural network to speed up the simulations. And well, as I said, we extract from the simulations some kind of data set, which you can see on the video that I'm showing, where we are only studying for now the velocity magnitude. And we're going to use some kind of autoencoder scheme to work in the latent space. So in the end, we have our data set, which is the video, for example. We encode it using the encoder, as its name says, to arrive to some kind of latent space, which is a really reduced space with way less computational cost attached. And we are going to work there. We're going to do predictions there or whatever we need. And then we need some kind of decoder to go back to the big space where we again have the reconstructed data. So with this idea in mind, we constructed some kind of autoencoder from one reference, which using some kind of mixing of convolutional layers and dense layers, we can downsample the space up to some latent dimension, really small, where we can work in a really reduced dimension. So in the end, the general idea of this neural network is to take a snapshot, encode it to latent space, predict in this place using some kind of architecture which we're working on, and then decode back the predicted states. And this way, we would be able to use this kind of neural network for prediction. Of course, for the training, we need to compute the loss we have in these kind of predictions, but afterwards, we will use this to just obtain these predictions. And well, finally, the last part of my thesis will be the reduced order models, where we're going to use some HODMD or well, model decomposition algorithm based algorithms. But first, let me again give some kind of guidance through these reduced order models. In the end, what we want to achieve with these reduced order models are the same, practically the same as in the autoencoder. We have our big space in the top part in the top images. We have one snapshot and the correlation between the different snapshots, the correlation in time, right? And what we want to obtain with these reduced order models is to go to a more reduced space where we can represent our database in a reduced manner, and also not only one snapshot but also the correlation between the different snapshots. So in this is pretty similar to what we're trying to do with the autoencoders, but in this case using model decomposition. And the advantages of this can be the cost reduction, since we can get rid of big part of the dimensionality of the database. We can use it also for denoising. And finally, for feature extraction, such as if we can analyze, for example, using singular variable decomposition, the most energetic mode, which is the mean flow, we can see that is related with the outflow. But if we analyze further modes, we can see something related to the inlet, then something maybe with the recirculation. So we can use it also for this kind of feature extraction. And well, why is this so important, this kind of pattern identification and this feature extraction? Well, in this slide, I want to convince you of that, since as you can see, and I've been repeating quite a lot, in a healthy heart, we have this kind of big recirculation that goes down to the apex of the ventricle, and that would mean we have a healthy heart. But when our heart has some kind of disease, there is some kind of impaired flow happening inside the ventricle instead of this kind of big recirculation, which then the flow adapts to this and creates this kind of stiffening and like different smaller structures inside until there is a progressive adaptation of the muscles of the heart, and for example can end in some kind of dilation of the ventricle, which is now a irreversible problem in the heart, creating this again big recirculation but with little vortices in the walls or whatever. So what many studies says is that first the changes because of a disease heart appear first in the flow and then in some kind of physical form. So if we are able to identify this kind of changes in the flow, we will be also helping some kind of classifying and prediction of these heart diseases. So as the conclusions is basically what I've been saying in this whole presentation. Our DigitHeart project is trying to develop tools that can help us treat preventively heart diseases. Also, for this, my PhD thesis is centered into obtaining simulation data of these cardiac flows to help improve the accuracy of this manual network of classifying and prediction. For that, we also need the help of these neural networks, which can speed up the simulation since some of them can be really with high computational cost. And finally, we can also do some kind of pattern analysis that can make us understand better than the underlying physics and also detect these kind of features that are maybe hidden to our eyes and can help us identify and classify some possible heart disease. So that was all. And again, our group, Model Flows, has this kind of model decomposition and deep learning tools, which you can find on the link in the video and also in this QR. So, well, also if you have any question, you can contact us from our emails or whatever, or even in the comments of this video. So, well, thank you all for your attention.